All right, welcome to this explainer. Today, we're unpacking a concept that is absolutely foundational for all you science students out there. We're taking the invisible forces of the physical world and breaking them down. We're talking about kinetic energy, literally the raw power of movement. And we're going to explore it both conceptually and mathematically, so you can totally master it.
Okay, here's our roadmap for today. We've got 5 main stops: defining kinetic energy, kinetic versus potential energy, the equation itself, actually calculating it, and finally, those crucial speed and mass multipliers. Let's get right into it.
Section 1. Defining kinetic energy. So, the most crucial thing to remember here is that the word kinetic literally means motion. It actually comes from the ancient Greek word kinesis. When we talk about kinetic energy in physics, we're strictly talking about the energy an object has entirely because it's moving. Basically, if it's moving, it's got this energy.
Think about some everyday examples. You've got a fast-moving car cruising down the highway, right? Or a bicycle speeding down a steep hill, or even a football flying through the air after a perfect kick. What do they all universally share? They all possess kinetic energy, simply because they are in motion. The motion itself is the energy.
And that brings us to this golden rule. It sounds incredibly simple, but trust me, it is so easy to overthink on an exam. When there is motion, there is kinetic energy. No motion, no kinetic energy. If that speeding car slams on its brakes and comes to a complete dead stop, its kinetic energy drops to absolutely zero. A totally stationary object has zero kinetic energy.
Moving on to Section 2, kinetic versus potential energy.
Now here's where the physics gets incredibly fascinating. An object's kinetic energy is purely about its own isolated movement. Like, if you imagine an object moving in a total void, completely ignoring everything around it, it only has kinetic energy. But obviously, in the real world, objects exist within systems, right? And when you factor in those surroundings, an object can have both kinetic energy from its motion and potential energy based on its position within that system.
Let's ground this with a massive real-world example, an airplane. So you have a commercial jet flying high above the Earth. Does it have kinetic energy? Absolutely yes, because it's hurtling through the sky at hundreds of miles an hour. But it doesn't only possess kinetic energy. Because it's up there at a certain height above the ground, right inside the Earth's gravitational field, it also has gravitational potential energy due to the Earth's downward pull.
And this exact same concept scales brilliantly down to the microscopic level. Take a single, solitary, moving electrical charge in empty space. It's moving, so, yep, kinetic energy. But place that exact same moving charge inside an electric field, and suddenly it's part of a system. Its motion is now being affected by an electric force. So in that field, it possesses its kinetic energy plus electric potential energy. The big takeaway here, kinetic energy is about the object's movement, potential energy is all about the object's environment.
All right, Section 3, the kinetic energy equation. This is it. This is the core formula you absolutely need to commit to memory. Kinetic energy is equal to 1/2 of the object's mass multiplied by the square of its velocity. Basically, mass times velocity squared, cut right in half.
But before we actually start crunching the numbers, we've got to remember the parameters of what we're actually calculating. Energy is a scalar quantity. In physics, that means it only has a magnitude, a size. There's no specific direction involved. And the standard SI unit we use to measure kinetic energy is the joule. So remember, your final answer is always going to be a number of joules.
Section 4. Calculating kinetic energy.
Okay, wait. Beware of this classic trap. I see students miss this all the time. The formula strictly requires standard SI units. You must always ensure your mass is converted into kilograms and your velocity is in meters per second before you plug anything in. If a problem gives you grams or kilometers per hour, you have to convert them first. Seriously, don't forget that step.
Let's look at a real calculation. Consider a highly modified super-light racing truck. Let's say its mass is 200 kilograms and its velocity is a blistering 80 meters per second. We just follow our steps to plug those exact values right into our equation. So, kinetic energy equals 1/2 times 200 kilograms multiplied by 80 meters per second squared.
After doing the math, squaring the 80 first to get 6,400, then multiplying that by the mass of 200 and cutting the whole thing in half, we arrive at our answer. 6.4 times 10 to the 5th power, or 640,000 joules. That scalar value represents the raw kinetic energy of that specific vehicle moving at that exact speed.
Section 5. the speed and mass multipliers.
Now, this reveals a truly profound truth about how the universe actually works, because kinetic energy depends on the square of the velocity. Doubling the speed doesn't just double the energy, it increases it by a factor of 4. Crazy, right? If speed increases 3 times, the energy increases 9 times. It is exponential. Meanwhile, the relationship with mass is direct and linear. Double the mass, you just simply double the energy. So speed has a much more dramatic impact on energy than mass does. Keep that in mind for your multiple choice questions.
I really hope you've grasped the foundational concepts and the math of kinetic energy today. As you walk away from this explainer, I want you to ponder this. What if the objects moving around you right now just suddenly doubled their speed? Think about the invisible, exponential power of motion in your everyday life, and just how much raw energy is generated the moment things accelerate. Thanks for joining me, and keep exploring the science all around you.